In this second video of the series, we're going to spend some time talking about very essential things that are interesting from inorganic chemistry point of view. As we know, when we started talking about concepts of organizing the human body, we stopped at the first step saying we have to recognize that there is a level which is called atom, and then subsequent step 2 would be level of molecules. At that time, I indicated that we're going to say a few more words about individual properties of certain chemical elements, but definitely the best way to start is to think about showing this slide and talking about the structure of a typical atom representing any kind of chemical element. As we can see, above diagram shows atom with an electron cloud model, and the lower diagram shows the same atom but using a different style of illustration, such as electron shell model. In the next couple of minutes, we will understand what the difference is. So let's first take a look at the central part of both diagrams and identify as a nucleus of an atom. Within nucleus, only two different subatomic particles could be found. Either they are positively charged particles, they're called protons, or they're particles with no electrical charge, and they're called neutrons. Mind you, the simplest chemical element, the hydrogen, would have no neutrons in its nucleus. It is going to have just one proton within it. And of course, further away we go from a hydrogen, we'll be able to see larger atoms with number of protons and neutrons reaching levels that are greater than one, that's for sure. However, number of electrons with a negative charge added to them should be the one which matches the number of protons, because overall, atom is considered to be electrically neutral for any given positively charged particle, proton. We should have the same number of negatively charged particles or electrons. So, how does it really work? Electrons travel at unimaginable speed around the nucleus, and therefore, when we see it as the electron cloud model, we really do not know exactly what this cloud represents. But on the diagram below, we can now start thinking about this. Assuming that atom, which is used to illustrate, would have 6 protons in its nucleus, therefore we make immediate deduction that there should be 6 electrons that are orbiting around the nucleus. Why do we have these two concentric rings? They're called electron shells. And the first electron shell of all atoms actually is fully saturated with electrons if it contains 2 of them. Should it have just one, it would be unsaturated. So number 2 gives stability to this electron shell, and then remaining 4 electrons are seen circulating around nucleus in the second electron shell. Now, if we ask ourselves a question, is this second electron shell fully stable? The answer to this question must be no, it's not. Because the second electron shell would become stable only if it contains 8 electrons. It cannot fit 9 or 10, so 8 is the maximal number for the second electron shell to gain stability. And if it has one less, basically that atom would be looking for an opportunity to get the missing 8th electron. That'll make it chemically more stable, but practically will become with one additional electron compared to a number of protons. The next slide is likely going to shed even more light to this. So for now, we just have to remember nucleus of an atom is made of protons and neutrons. protons have a positive charge, and matching number of electrons should be seen around nucleus orbiting, and total number of electrons should be equal to number of protons. Let's see the next slide. Here is the simplest chemical element, that is the hydrogen. I mentioned that it has only one proton in its nucleus, and therefore it has to have just one electron that can be only placed into first electron shell. So knowing that first electron shell would become more stable if it contains two electrons rather than just one, that explains why hydrogen is practically almost always looking to find another chemical element and to get into chemical reaction to make itself part of the molecule within which it'll gain more stability. The best example is seen throughout the world. It's the molecule of water, which requires two atoms of hydrogen to bond to a single atom of oxygen and then to make a molecule of water, H2O. By stepping into this chemical reaction, both hydrogen atoms as well as the oxygen atom will gain this kind of additional stability and will prevent molecules of water being dissipated left, right, and center whenever condition allows for that. Water, for that reason, becomes quite stable molecule, although it is made essentially of atoms that have different levels of being relatively unstable. Let's see here, carbon is 6 protons and 6 neutrons. Therefore, its 6 electrons could be seen arranged, 2 of them in the first and 4 into second electron shell. Now, we know that second electron shell would be more stable if containing 8 electrons, and the carbon itself, for that reason, will be in a very favor of becoming part of the larger molecules, binding to other atoms in order to gain stability, and we're going to experience this throughout the world of both inorganic as well as organic chemistry. In a periodic table of elements, there will be a separate column that is composed of what we call noble gases, like helium, like xenon, like many others. Why do we call them noble elements? Because they are having electron shells that are fully saturated with electrons. And for that reason, noble elements do not have the same propensity to step into chemical reactions as quickly as other chemical elements. If we see here example of nitrogen, which is with 7 protons and 7 neutrons, of course we know it has to have 7 electrons, 2 in the first, but 5 in the second electron shell. So practically seeking for 3 more electrons to gain somehow, and the nitrogen will become much more stable. Oxygen with 8 protons and 8 neutrons, of course, have to be matched with 8 electrons. 2 in the first, 6 in the second electron shell. Therefore, oxygen is also looking for 2 extra electrons, so it'll gain stability being part of the molecule. Along the same line, you can see here that atomic number 1, 6, 7, or 8 actually corresponds to number of protons within the nucleus. But the mass number is 1 or 2, 12 or 13, 14 or 15. So how do we get to 12? Protons and neutrons are larger particles, they have a mass. So of course, when we add 6 plus 6, we're going to get the total of 12. Why occasionally 13? Because in nature, natural isotopes of carbon could be found, which would still contain 6 protons. However, there will be the 7th neutron added. Therefore, its mass number will go from 12 to 13. And atomic mass of hydrogen, for example, would be just 1 with addition of 1 extra neutron. it may go to 2, and this is also an event which is happening semi-regularly in nature. That's why these atomic mass numbers are always some kind of odd decimal points. Why? Because of interaction between total number of, let's say, regular typical atoms and their isotopes are found in the nature in this kind of ratio. So that brings average atomic mass to become 1.01. It's not a mass of electrons, it's a mass that is sometimes seen because of extra added neutron into the nucleus. In the lower part of the diagram, we can see the sodium, the chlorine, potassium, iodine, and now we can see opening of the third and eventually fourth and fifth electron shells. So let's see what's going on here. In the first electron shell, 2, in the second electron shell, 8, in the third electron shell, just 1 electron. That's the sodium. And this single electron, of course, is going to be explanation for us why sodium is also very quick to step into a variety of different chemical reactions. In order to gain its own stability, it would prefer, and it would be much easier, to get rid of this sole electron from the third electron shell and to donate it to some other atom than to look for gaining of additional 7 electrons to make the third electron shell stable. Chlorine is quite the opposite, and I hope that you can already see how these two chemical elements are going to really work it out together. It has 17 electrons, 2 plus 8 plus 7. In a third electron shell, chlorine would love to gain 1 more electron that sodium would love to donate. And as the chemical reaction is going to happen between sodium and a chlorine, we're going to get a molecule of table salt, 1 atom of sodium, 1 atom of chlorine, and it is something that all of us would recognize as a crystallized molecules that are seen within every single kitchen. One of the basic ingredients that we have to keep adding to our food. Is table salt stable? Does it disseminate sodium separately from a chlorine ions? No. It can dissolve within water, but dissolving it is something different than expecting sodium and a chlorine to simply separate while kept in a dry and cool place. Potassium already has 3 electron shells, which are filled up with 2 plus 8 plus 8, so 18 electrons. And its fourth electron shell should have at least 1 extra dark dot, which is not illustrated here. That's why I'm asking if you can add it. That would be even better and nicer. We can try to do this together. So I'm just going to use the pen and add 1 more electron into its fourth electron shell. So sodium as a potassium would have the same idea. Let me try to get rid of this electron and to gain more stability being part of molecule. Iodine, now big, huge leap forward with 53 protons and 74 neutrons. So basically you see here 2, then 8 electrons. Third electron shell can contain up to 18 electrons. That is also going to add to its stability. The fourth one as well, but the outermost, the fifth electron shell of iodine would have 1, 2, 3, 4, 5, 6, 7 electrons. So iodine would be also looking for 1 extra electron to be added into its outermost fifth shell. That would make it a little bit more stable. We don't have to bother with atomic numbers, with mass numbers. So I just wanted to give you an idea of what these numbers represent. And now with this idea and this kind of knowledge we acquired, we can take a look at the next slide and try to see what's happening here. Oxygen molecule would be stable and as such exists in the air that surrounds us in atmosphere. How is it done? It is done by oxygen with its 6 electrons in a second shell, clearly looking for 2 more electrons to gain. So other oxygen molecule, oxygen atom, also having 6 electrons, cannot opt to donate 2 and leave itself with just 4. It would not cut. So in this case, what is done is example of so-called covalent bonding, which simply explains that 2 atoms of oxygen have 2 pairs of electrons, which they share. And sharing is happening at the speed of light, speeds unimaginable to us. So practically at any point of time, we can say that either of the 2 oxygen atoms would be seen as having 8 electrons orbiting in their outermost shell. That'll confirm oxygen molecule as being stable and would not dissipate into 2 individual atoms of oxygen, which would not be helping us to breathe. We need molecular oxygen to breathe. We don't need atomic oxygen. Sometimes when bonding happens, although 2 pairs appear to be shared, there is one unpaired electron. And in this case, we're talking about superoxide free radical, which we know is not the same as the molecule of oxygen. And this kind of bonding would not be beneficial to human body. Obviously, I already started talking about bonding between different chemical elements, between different atoms representing it. So we're going back to this example, except this time it's nicely illustrated. And we're talking about type of bonding that we simply call ionic bonding, which is typical for inorganic chemistry. It would not be seen regularly in organic chemistry. We'll find out why. So if we go with one single atom of sodium, we know that it should have 11 electrons. Doesn't matter any longer what is in its nucleus. It is 11 protons, but we're now really concerned with these electrons. In a third electron shell, there is just 1 electron, which makes this shell being unstable. If sodium atom somehow finds a way to donate that electron, it will lose the third electron shell. It'll have just 2, totaling 10 electrons versus 11 protons. Sodium will become its own ion, charged particle with 1 electron less than what naturally appears to have. So positively charged ion, but it is not going to be disaster. It is going to be our preferred way of seeing things. Let's take a look now at the atom of chlorine. There are 7 electrons in its third electron shell. Gaining 1 more would make it more stable. Therefore, there is a good reason to believe that chlorine will accept this electron if there is suitable donor. In this case, suitable donor is atom of sodium. As the chlorine atom added 1 extra electron, keep in mind now we have 2 plus 8 plus 8, 18 electrons, but only 17 protons. Therefore, this becomes ion of chlorine with a negative charge because of that kind of 1 extra electron being added. Now we're back to basics. We know that opposites attract. Positively charged particle, ion of sodium, wants to stay as close as it can be with a negatively charged particle, calling it chlorine ion. And this form of electrical bond, what we call ionic bonding, is actually what's going to hold together sodium and chlorine, and they would form the crystallized form of table salt as we are seeing it at the bottom of the picture. I apologize, I clicked accidentally something else. So it is going to create a bit of a network, pretty much regularly shaped in between larger yellow-colored chlorine ions. We're going to see smaller green-colored ions of sodium forming crystals of table salt, or chemically calling it the sodium chloride. This explains practically what is the essence of ionic bonding. Now, let's put a little bit of table salt into a glass of water. What's going to happen to it? We know the answer is it will dissolve. We wouldn't be able to see crystals of table salt at the bottom of a glass. If we stir it, it is going to happen even faster. If we see the solution, it is going to look very much the same, just as a glass filled up with water. But if we try to drink it, it's going to be salty. So we have to find out what's going on, what happened. Basically, ionic bond is good, but in a certain condition. It is going to break and allow separation of ions of sodium to go this way and ion of chlorine to go this way. Molecule would separate. If we think of this, basically, we're going to find out this as the most direct answer to question, why do we have so many ions of sodium, potassium, chlorine that are freely found within any fluid-filled space within a body, whether it's filling up the cell or just filling up the immanent cellular surrounding? Ionic bonds are not excessively stable, so water will be able to break them down. And as a result of this, we're going to have significant ionic content being found within a cell or in the fluid-filled compartment which surrounds the cell. In a sharp contrast to ionic bonding, we can have a different idea how two atoms or more can bond together, but become a little bit more stable as the molecule. Water will not dissolve them. So a simple example illustrates two hydrogen ions with single electron shell with 1 electron each. And we know that electron shell number 1 would be more stable if accidentally somehow we have 2 electrons. So joining forces and creating a single covalent bond between 2 atoms of hydrogen makes the hydrogen molecule, which now gains stability because these 2 electrons are seen as evenly circulating around both nuclei. Therefore, if we're to write it down, we can put H and H, symbol for 2 individual atoms, and connect them with a straight line, simply saying that this straight line means 2 atoms share a single pair of electrons, and that is the covalent bonding. If we want to simplify it, we just put symbol H for hydrogen, subscript 2, to identify it as a molecule of hydrogen composed of 2 atoms of hydrogen. Oxygen atoms would do the same, except they have 6 electrons in the outermost shell. So practically each of the 2 atoms would require 2 more electrons to gain stability. They're going to do it by allowing their shells to partly overlap. And they're going to share 2 pairs of electrons that will be freely circulating around either of the 2 atoms within a molecule. O, symbol for oxygen, 2 straight lines, practically identifying 2 pairs of shared electrons. So this is double covalent bond, molecular formula O subscript 2. If we try to see what's going to happen with nitrogen atoms, they would have just 5 electrons. So obviously we're going to see here an example of 2 nitrogen atoms within molecule of nitrogen sharing 3 pairs of electrons. So 3 lines identify 3 triple covalent bond, but it's still N subscript 2. In order to avoid conclusion that covalent bonding could only happen between atoms of the same chemical element, like 2 hydrogen, 2 oxygen, or 2 nitrogen, let's see this. And this is going to be practically seen throughout the organic chemistry. As we know, there is no organic molecule which doesn't contain at least a single carbon atom. Carbon, as we already know, will have 6 electrons, of which 2 in the first, 4 in the second electron shell. We would prefer to have 8 of them. So that means carbon will have to make multiple covalent bonds in order to gain somehow extra electrons that will be seen as making 8 in the second electron shell. So in this example, which is easy to follow and easy to understand, single carbon atom will be seeking 4 individual hydrogen atoms, all having 1 electron in its one and only electron shell. So when they form covalent bonds, carbon to individual hydrogen atoms, basically we're going to see here 4 pairs of electrons that are shared within this molecule, equally belonging to either of the hydrogen atoms or to carbon atom being in the center part of the molecule. So the situation looks a little different. We don't put 4 parallel lines, but rather we keep here, if we're writing structural formula, carbon in the middle, and each of the red lines identifies a single covalent bond generated between carbon and those 4 individual atoms of hydrogen. Molecular formula CH subscript 4 to confirm that within molecule we need single carbon but 4 hydrogen atoms to make it molecule of methane, one of the gases that unfortunately is frequently found within mines and becomes major risk for explosion because it's combustible gas, unfortunately have taken too high toll on lives of so many miners worldwide, because it is not just ready to ignite, it creates a massive explosion. Now, as we have already acquired sufficient knowledge about understanding what covalent bonding is, if we just see 1 oxygen, 2 hydrogen, we know what's going to happen. They will create 2 different covalent bonds. So we can write it down like this. Molecule of water can be illustrated like atom of oxygen with individual covalent bonds binding 2 different hydrogen atoms. Now, what's happening here? The nucleus of oxygen atom has 8 protons, while hydrogen atoms would only have 1. Inevitably, when they create a bond, this pair of electrons will be shared, and this pair of electrons will be shared, making individual covalent bonds. Now, you just have to think of this as 2 siblings being born 4 or 5 years apart from each other, and they still play together. But when one of them wants specific activity and the other one doesn't, who's going to win? Younger or older sibling? You know the answer. It's going to be older sibling that wins most of the time. So in this case, we do not see oxygen as being older sibling. We just see it as nucleus, which has power of 8 positively charged particles to be a little bit stronger than nuclei of hydrogen with a single positively charged particle called a proton. That would mean, although they share a pair of electrons, oxygen will attract them a little bit more regularly than the hydrogen atoms would be able to do it. Therefore, some kind of electrical charge develops on the surface of the molecule. Part with the oxygen becomes more negatively charged, or we can say just more frequently with a negative charge, while the hydrogen ends become a little bit more frequently with a positive charge because the electron is away from this hydrogen nucleus. As a result of that, we consider that water molecule is polarized. You can use example of regular AA or AAA size batteries for remotes that we use in our households. And we know that each of the batteries will have positive and negative end terminal. Although it's a single battery, its two ends are showing different electrical charge. So that idea we can use for these molecules that we also consider to be polarized. And this is not going to be their disadvantage. It is going to be practically a major advantage, not only for a molecule of water that will become universal solvent, but also for other particles. They could be easily dissolved by water. Let's find out what is on the next slide. And here is example of hydrogen bonds. Since you already have the idea of what water molecule, a single molecule, looks like, now we can consider that between individual water molecules, there are some kind of bonds. For example, if you drop a single droplet of fluid on the table in front of you, basically it will remain a single drop of water until it evaporates. You would not be able to see individual water molecules dispersing all around the table. It will remain practically a single drop that you can see and identify. I think this explains it quite directly. Cohesive forces that hold molecules of water together are exactly those electrical charges which generate so-called hydrogen bonds. More positively charged part of the molecule exposing hydrogen is going to be electrically attracted to more negatively and of another molecule of water where the oxygen is found. Same here, I'm just adding negative signs to point out that this is more negative part of the water molecule. And this one here, of course, because it's a hydrogen, is going to be with more frequently positive charge encountered. So with hydrogen bonds, molecular waters are held together, making water quite solid and quite steady, even if it comes in a pure form that we have in front of us, just a glass filled up with water, 100% water, no other particles to be found within it. So we know that human body is made 60% out of water. And therefore, we really have the obligation to understand what water is, because if we don't understand what kind of benefit it brings to the human body, basically all physiology concepts could be much more difficult to understand. So we already formed in the past few slides individual molecules of hydrogen, and we know how to form individual molecule of water. I mentioned that these bonds are quite solid and not so easy to break as ionic bonds, for example, but it doesn't mean that they are absolutely inseparable. When we have two proper reactants that are ready to kind of change their relationship and to result in building something that is more complex, they're going to get into chemical reactions. So two molecules of water with one molecule of oxygen, two molecules of hydrogen, with one molecule of oxygen, when they react with each other, the end result is going to be production of two molecules of water. So we can say this would be useful, we can breathe, but right now, other than to experiment with hydrogen operated engines instead of engines with internal combustion, we would not really have so much need for molecules of hydrogen continuing to exist on this planet. Therefore, we would benefit from water, whether it is water that's going to be consumed by us to rehydrate the body and body, which will fill in our cells, or it's going to be just extra water that will fill in the lake or river or oceans, where we're going to enjoy a little bit of summer relaxation and refreshment. But that is what generates the water in such a copious amount as we see it throughout the world. Now, finally, to explain this idea that the water, as the universal solvent, can easily break ionic bonds. We know that in generating crystal of table salt, we had to put together positively charged particles of sodium next to negatively charged particles of chlorine. So their electrical charge actually made them come together. Now, when you add to this, let's say, mixture, another molecule or molecules that are exhibiting their polarized structure, guess what? It's going to be a bit of competition, because positively charged sodium will be attracted to go towards negatively charged end of the molecule of water. And so would negatively charged chlorine ion evenly attract multiple molecules of water with their positive charge end, where the hydrogen is, to surround it. And that is explaining why water was able to break this bond, practically separating chlorine from sodium, surrounding individual sodium ions, individual chlorine ions with multiple water molecules. Please remember that separating them did not actually bring their electrons, one back to sodium, one less to chlorine. They remained in an ionized form. So if we say, for example, we have solution and we would let water evaporate due to heat, what's going to be left inside the glass? Sodium and the chlorine. And at the bottom of a glass or a container, we would still observe formation of crystals of table salt. So this chemical reaction is completely reversible. Of course, it's not only the table salt that dissociates within our body. Many other chemical elements would dissociate. What we consider table salt being a salt, very similar idea we can see here with formation of potassium chloride instead of sodium chloride. It is also salt, which when submerged into liquid, which dissolves it, yields practically equal number of potassium and chlorine ions. But they would remain separate, giving this solution also electrical neutrality. But there are other inorganic chemical molecules which, when allowed to dissociate, they yield high content of hydrogen ions or hydroxy ions. Hydrogen ion is with a single positive charge. Therefore, molecule of hydrochloric acid basically yields hydrogen ions, and the total amount of these hydrogen ions are contributing to acidity of this solution. On the other side, potassium hydroxide, if allowed to dissociate, yields larger number of hydroxy ions, OH, with a single negative charge, and these ions are contributing to alkalinity of the solution. Strictly speaking, in a chemical form, we have a pH scale which is from 0 to 14. The value of 7 would be exact chemical neutrality. So it's neither acidic, neither alkaline. 7 is neutral. So for this solution of salt, whether it's potassium or sodium salt, the pH will be 7. There is no surplus of hydrogen or hydroxy ions. It's only potassium and chlorine. But on the other two examples, we're going to see increased number of hydrogen ions. So acidity will go from 7 downward towards 0 as the acidity levels are increasing. So lower the number, acid is stronger. For bases, we go from 7 up to 14, and we would say that higher the number, basically the alkalinity of a solution is increasing. Neither acids or bases are always welcomed within a human body, as their increased concentration and change in the optimal pH value of the entire body would start seeing increased acidity or increased alkalinity, resulting with certain damages done to the body. Why I said, strictly chemically speaking, 7 is considered neutral. Yes, that is the principle of inorganic chemistry. But for human body, the pH value of in between 7.35 to 7.45 is considered to be optimal homeostasis, and we consider this to be ideal or chemical neutrality that the body operates best when pH of any of the body fluids is within 7.35 to 7.45. If it goes less than this, towards 7 or below 7, we're talking about acidity, or if the value increases to 7.5 or higher, we're talking about alkalinity of the body. Here is a diagram which illustrates what we just talked about. 7 is neutral, but this is strict inorganic chemistry. We have to think 735 to 745 to apply this concept to human body. But as we can see here, increasing number of hydrogen ions increases acidity, and increased number of hydroxy ions in the solution is going to increase the alkalinity. Please note that these are all powers of with a negative value. So that is why we're seeing increase in acidity going this way from center to the left, and increase of alkalinity going from left to the right side of the screen. At this point, we're coming to conclusion, and we can say we did not dwell into details of inorganic chemistry, but I hope that for the start, just to understand some of the basic principles, such as ionic bonding, such as covalent bonding, such as hydrogen bonding, is something that we have done successfully. And of course, understanding what leads to the formation of different molecules and their dissociation into chemically neutral or acidic or alkaline solutions would help you move on. And our next chapter will be essentials about the organic chemistry. Once again, thank you very much for watching this video.